Hello. How are you doing today? So we would like to thank you. You could be anywhere else in the world right now, but you're here with us. We appreciate that. Moreover, it's 4 o'clock, and you've just been drinking probably.
No.
I see some guilty faces. Please stay with us. We will try and make it worth your while.
We will make it worth your while.
So, we are New Knowledge, and we are in the business of protecting the integrity of the information ecosystem. So another way to say that is we protect highly visible, responsible brands from the effects of disinformation online. So you may have heard, or you probably know, that fake or false information is a lot more likely to be spread online than true information. In fact, I think the figure is 70%. So this is where we come in. We work with our partners, including the Department of Defense, DARPA specifically, to build various tools that we can use to analyze activity online, detect anomalies, report them to the affected brands, and help them fight it. More specifically, we work for a subdivision of New Knowledge called NK Labs, and our job is basically to push the state of natural language processing forward, contribute to that, bring tools from that cutting edge back into the company to help address this problem. So in the work we do, as I just mentioned, it's helpful to have some kind of software that can read natural language and classify the text coming in from whatever social media platform you're interested in, classify it into, something anomalous, something non-anomalous, spam, not spam, fake news, not fake news, or some variant of that. And this tool helps us achieve that. So specifically, we'll be talking about character-level convolutional neural networks for semantic classification. I'm Paul Azunre.
I'm Numa Dhamani.
We are NK Labs.
So, what is text classification? At a very high level, text classification is the process of assigning predefined categories or tags to a document. Semantic classification helps you identify key concepts or context of a document. So this has many applications, including sentiment analysis. So let's say you want to look at the content of reviews on Yelp and be able to classify them as positive or negative. Also topic labeling. So you want to be able to take articles or documents and categorize them into predefined categories. Or even the detection of spam or non-spam. So today we would like to introduce Simon. Simon stands for Semantic Inference for the Modeling of Ontologies. It's a mouthful, I know. It's an open source classification tool, which means you all can use it. It's available on GitHub. It's a character-level convolutional neural network, as opposed to a word level or sentence level. And this should be emphasized because this enables misspellings and other social media features such as emojis to be naturally learned. It is an auto-ML system that's motivated by DARPA's Data-Driven Discovery of Models program. So what this program is essentially trying to do is that they want to build an automatic data scientist. And the idea is that to the system you would provide some sort of natural language input, be able to figure out the problem that it's asking, do the necessary pre-processing feature engineering steps, apply machine learning algorithm, and then be able to communicate the end result in a natural language to the user. I think earlier today, Graham talked in his talk, about how AutoML systems are the future of data science, and one of the tools he mentioned, feature tools, actually came out of DARPA's D3M program. So it's a pretty cool and complicated problem, and where Simon comes in is that it is able to take a tabular data set and semantically classify it into some base classes. And we can use those base classes to do appropriate analysis. So let's say you have a float column and you can use it in a regression task. You have a categorical column, you can use it in a classification task. Another really unique thing about Simon is that it relies on transfer learning, which is still relatively new in the natural language processing space. So we'll talk more about this later, but what Simon essentially does is that it learns an initial set of weights from some simulated data, and then transfer learns on hand-labeled collected data sets from CCAN. And what this does is it improves the weights, and because of this, we're able to account for realistic data imperfections, and also rapidly expand the set of classes with minimal labeled data requirements.
So, of course, when you first start working on a problem like this, you want to compare yourself to existing methods. So let's talk about some traditional text classification algorithms. How have people approached this in the past? One thing, or typically what people do is they take the text segments and try to generate some features based on them. They may use a word-to-vec model, for instance, to create a vector, or they may use a word-ordered combination n-grams of some specified length. And once they've obtained those features, they train some classical classifier on top of them. It could be a logistic regression, it could be a random forest, and there are, of course, a lot of variations of this idea. But most, if not all, of them have some very particular characteristics. And this is what we try to contextualize on this slide. So, first of all, they use a knowledge repository of some sort. So in the example I just gave, it would be a word-to-vec model, which you first have to train on a huge corpus. There's a lot of feature engineering that goes into the process. So the particular features you choose are very, determinative of what will happen in terms of performance. So a lot of time is spent picking the right features, and there's a lot of manual effort that goes into that. And particularly, it's also very specific to a language or style. So if the language changed from English to Chinese, obviously you couldn't use your word-to-vec model anymore. If the style changed and you moved from Twitter to Facebook, the speaking style changes, and these models break down right away. If you're using emoticons, right, that's not really a word. So how will a word-to-vec model generate features based on that? Slang, right? The meaning of words change all the time. So again, if you train that kind of model in a space, one space, and then that stuff changed, your model will fail. So all of this stuff is really what motivated us to pick a convolutional character level neural network to address this problem. We saw a paper in NIPS that did this at the time we were starting. Oh, oops, I think it's New RIPS now. But we saw a paper in that conference, and it argued that at the character level, convolutional neural nets don't have any of these issues. So why transfer learning? And I may be beating a dead horse a little bit at this stage. You have heard a number of excellent talks that talked about this. So the idea is that you can train a model in one space where you have a lot of labeled data readily available, right? And after doing that, let's say you want to address another problem in domain B where training data isn't as readily available, so you're able to use the initial knowledge basically to improve your performance and reduce some of the computations that you would have to do in domain B. And of course, you still need training data, it's just that you need a lot less, and less computing and so on. And what needs to be, I guess, stressed is that this problem came out of computer vision, image analysis, and a lot of really cool stuff has been done in that space. But when it comes to natural language, it is less explored. So one of the things that this work has accomplished we argue, is provide further evidence on its efficiency in this space, text analysis, as opposed to image analysis.
So Simon is defined as a multi-class and a multi-label classification problem. And this is unique because a lot of state-of-the-art and popular algorithms that we all know and love, like pandas, are single class problems, right? So what multi-class means is to be able to classify something into one of 3 or more categories. But what Simon can do is also classifies as a multi-label problem, which is exactly what it sounds like. You can classify it into multiple labels. So let's say you had a column A with a city name on every single row. So your row 1 is Austin, your row 2 is New York, your row 3 is DC, your row 4 is LA. And Simon would be able to classify that as a city, a name, and text. So how does Simon work? Simon's overall architecture consists of 2 main components. The first network encodes each individual sentence. So this connects 13 convolutional, max pooling, and fully connected layers. The second is a network that encodes a document as a whole, connecting 7 layers. Next, we'll briefly walk through the diagrams of these networks. But if you're really interested in the architecture, our paper's up on Archive, where we discuss it in a lot of detail.
So what you're looking at here is the visualization of the architecture. And don't worry too much about the details, just the general picture. So text comes in on the left side. It gets one hot encoded. The one hot encoding, it's critical to mention, happens in a layer as opposed to a dimension in your data. Memory advantages to that. Then it goes through some convolutional layers, a stack of them, some max pooling layers, some dropout to reduce overfitting, all the standard stuff you guys know about. And then finally there's a fully connected layer that maps that into your space of categories, equal in dimension to the number of categories you're interested in.
So in addition to convolutional neural networks, we also use bidirectional long short-term memory networks, also known as LSTMs, which are a special kind of recurrent neural networks which are capable of handling long-term dependencies, which traditional recurrent neural networks aren't able to do. But why bidirectional? So the problem with a lot of these networks is that they look at previous timestamps to be able to create representations. But in a lot of cases, especially a lot of natural language processing tasks, you need more context, so you need to be able to look forward. So let's say you have 2 sentences. The first sentence is, he said teddy bears are on sale. And the second sentence is, he said Teddy Roosevelt is a great president. So if you pick the word teddy and you look at the 2 previous words, he said, you don't know if he's talking about teddy bears or the president. So this is why you need to be able to also look forward, and that is what bidirectional neural networks accomplish. So there are 2 connections. The first is a backward layer, which is able to predict previous timestamps, and then a forward layer, which is vice versa.
All right, so we've shown you some of the components that go into this network. So now let's revisit this transfer learning idea. This is another picture. Input comes in on the left, output comes out here. This is the prediction for your category for the text. And I'll discuss this in the context of the problem that DARPA is interested in, the initial motivation for this work. So as Numa alluded to, DARPA wants to replace us all, basically. Well, the truth is, in my opinion, they're able to replace some of the tedious work we do, but not yet the interesting work we do. But anyway, they want to, in order to build an automated machine learning system, it helps to know what data type is coming in, right? So if you have categorical variables coming in, you can do a classification. If the float variables coming in, you can do a regression. If there are latitudes and longitudes in the column, you can put that on a map, and so on and so forth. It basically defines what kind of operations you can do on the data. So this is what motivated this problem. And in order to do the initial step, before the transfer learning step, we generated some fake data. That's easy to do. We generated data using the Faker library, you might have heard of it, for some of these classes that we described. So then we trained the whole network on it, took about 6 hours, something like that. And having done that, now we went and hand-labeled data, we labeled it in a semi-supervised way. We built some classifiers, we predicted the class, we then manually checked every single one of them to make sure it's correct. We had to fix a number of them, obviously. And having done that, then we froze these initial layers coming from the Faker trained model, and then relaxed these ones and trained only those on the hand-labeled data. And obviously, you're using just a subset of the parameters at that stage. And so obviously, you need less data to achieve the same performance. Yes, and of course, the reason why this works, people argue, is that the first layers in your network, your convolutional network, learn the general features of the problem. So the analog in computer vision would be learns the edges, how to detect edges. And as you move through the network, the features being analyzed are getting more specific to your problem. So in that sense, there's some general aspect of the classification that you can carry over or transfer between from the simulated realm to the hand-labeled realm.
So I know we spent a lot of time talking about how Simon works. So let's finally get some experimental results. So we performed the transfer learning experiment on Simon and got a test binary accuracy of 98.8%. The metric we're using is binary accuracy, which is the ratio of correct predictions. So that is true positives and true negatives over the total samples. So this was done with the geographical categories included for Simon. So Simon can also classify into geographical categories like postal code, country, city, latitude, longitude. But let's zoom in on the binary accuracy here. So I think what this shows is the effectiveness of the transfer learning experiment. So the first step of this, which is the training phase in like a light blue, so you see that it starts out there around like a 75%. And this takes about 6 hours. This is being trained on the initial simulated data on a NC6 machine on Azure. And after that, for the second step, you see that it starts out around like 88%, and this is a transfer learning step. And it shoots up to like 98% really fast. And this step only takes 1.5 hours on the same machine. So you can see the potential for transfer learning in natural language processing, because this shows us that that we can achieve really good results with minimal labeled data requirements and improve our accuracy.
And one thing I would like to stress is that in performing the transfer learning step, we didn't need semantic alignment between the initial categories in domain A and categories in domain B. So the initial categories have very little to do with the categories we ended up training in the second transfer learning step, which is interesting. And in particular, some of the variables it worked for, like categorical variables, if you really think about it, classifying a column as a categorical column is based on statistical properties at the column level, right? So something is categorical probably because there are not that many unique entries in the column. So there's a lot of male and female, or there's a lot of white, black, right? So the ability of the neural network to capture those kind of properties, statistical properties at the column level, was interesting to us, or surprising.
So the next thing we did was we used DARPA's D3M's open source data sets, which were collected and manually annotated by MIT's Lincoln Labs. And we calculated a similarity score over 38 data sets. So we're defining the similarity score as a percentage of labels, which is where any of the annotations match the manual annotations. So you see that Simon achieves a pretty high similarity score of 92%. There was actually a data set I was looking at that were 92 columns, and Simon got like 100% similarity score, which was really impressive. But in some cases, I think that Simon actually outperforms the manual annotations in the sense that it provides you a lot more insight into your data. So there was a column which was labeled zip, and there were a bunch of zip codes, and it was classified as categorical through the manual annotations. But Simon accurately classified that as postal code. So I saw this a lot with countries, cities, even like Boolean and all sorts of columns. So you could say that the 92% is a little underestimated, and it should maybe be a little higher. So then we wanted to see how this compares to current popular tools for classification. So we used pandas D-types, and we got a similarity score of 71%. And you can see that Simon's annotations match the manual annotations a lot more accurately, like they're more closely. And also, I think it's important to emphasize that they provide a lot more insight into your data, being a multi-class and multi-label formulation. For example, like pandas would classify a lot of columns as objects or string, whereas Simon gave you a lot more insight into it, telling you if it was categorical or if it was a Boolean, which I thought was pretty cool.
All right. So we did the first experiment, it worked, we were celebrating, and then we wondered what else we can do with this. And somebody suggested an interesting experiment. Can you predict the age of social media users just based on the language they're using online? Maybe, maybe not. Let's see. Did it work? I think it did. So what you're looking at, binary accuracies, training, validation, and test. And initially when we saw these results, we were coming down from the high of 99%, right? So we were disappointed. But we checked the state-of-the-art methods for this problem, and we were surprised to discover that this is actually comparable. If anyone has any methods that do better than this for age prediction on social media, I would like to speak to you. But this is what we found. We found that the state-of-the-art methods do something around this. And here's the kicker. Those methods are using header information. They're using graph information. They're analyzing who the person is following online, what websites, and so on. Who are their friends, right? They're not just the content of the message. Whereas we were able to achieve comparable performance just by semantically analyzing the text at the character level, using that as a raw signal and attaining comparable performance to state of the art. Now this is profound because there are some applications where you may not have access to the header information. Of course, if you did, you would like to combine methods that use the content and methods that use the networks and all of that. But if you don't have access to that information, what we have done is shown that you can achieve comparable performance just based on the character level semantics of the text. So as you can see, the area under the curve is better than you would have otherwise. Looks good. So then, of course, we wanted to throw the hammer at other problems, and this one, of course, came up. Spam classification, spam or spam. So you've heard about the Enron data set. We took that, subsampled it, took 2% of the Enron data set. We took some subset of a large 419 Nigerian scam data set, we labeled that as spam. We did, all the usual stuff, training, testing, validation. And this is the performance we got after about 30 hours on one GPU. It actually ran out of epochs. I set it to 20 epochs and it ran out. And then it was time to give this presentation. So I'm pretty sure if I trained it on more than 2% of the data I have, and for longer, this will get to the state of the art of 99%. Again, the kicker here is that the state of the art is using header information. State of the art is using metadata about the user beyond the content of the message. We are just using the semantics of the message at the character level, and we are attaining comparable performance. And I'm only repeating it so many times because I think it's worth hammering that home. If you take anything away from this talk, is that please take away the fact that you can predict a lot about you just based on how you speak. It's kind of creepy at the same time, it can be useful. So if the situation this was useful in is in another DAPA program, and we got some data from JPL, email data, but of course because of privacy concerns, they don't want to tell you who received the message, who sent it. And so they strip all that information away, and that basically tripped up most of the program because all their methods depend on that stuff. Our stuff just stale too. So, cool.
So after Paul just sold you on Simon, I'm sure that you all want to try it out, and that's great because we developed a software implementation. It's a pip installable library written for Keras. It's available on GitHub, and it is able to scale to multi-GPU settings. We are currently developing a full heterogeneous server. Please use Simon. If you can think of any other potential use cases, if you would like to use it, or if you have any feedback, we'd love to hear from you. You can email us, reach out to us on LinkedIn, tweet at us. But yeah, use Simon. Of a lot of people. So we would like to acknowledge all the authors, which in addition to Paul and I were Craig, Jeffrey, Garrett, David, Rebecca, Sandeep, and Jonathan. We'd like to acknowledge DARPA. As I mentioned before, this work is motivated and supported by DARPA. And the contributions of all the researchers in the field, without which we probably wouldn't have picked a character-level convolutional neural network. If you would like to see our references, please see our archive paper. Please go on archive and see your paper anyway, even if you don't want to see the references. I think it's pretty good. But yeah.
And finally, the very important slide. We are hiring. If you're looking for the next gig and you heard anything here that sounds exciting to you, if you want to defend the very discourse of our society, please come join us. Time for questions. Yes.
I've just got a question about real-time latency. So, in real-time classification, how long are those model stations run?
Yeah, the hard part is the training. Deploying the classification is, it's very small, near real time. So it's Keras. Once you have the weights, making the prediction, it's very little time.
Cost more milliseconds, or?
Depends on the size of the model, but it can take milliseconds. Yeah.
Thank you.
Yeah.
So the description of Simon, to me, sounded very similar to the Elmo classifier. If you're familiar with it, can you speak to that in any way around the differences between them?
I am familiar with the Elmo classifier. Yeah, but it's. Do you have any details about what goes in it? I can guarantee it's not.
Yeah, no, it's fine. I mean, Elmo is also a character base. It's a DNN, I guess, instead of a CNN. But it's a deep contextual base, so it's got it's based on BiLSTM as well. So we're just curious. It's very similar to kind of what you've presented here.
I'm not sure if Elmo actually employs transfer learning.
Okay.
And I think that's something that's very unique to our model because I think that's very, again, not explored in natural language processing.
Mm-hmm.
And I think what Simon is doing is it's showing the potential for that in NLP as well.
Okay, cool.
And you look at, so you're doing character level, a lot of use word level. Can you speak to the
Yeah, so that drove the initial decision to pick the character level model. So a word-based model often is not as robust to misspellings, or it's not as robust to modern ways of expressing yourself on social media, including the use of emoticons, for instance. So the way you probably did the word level model is you built some kind of feature function that converted your word into some feature, right? And usually that feature function is trained on natural language, well-formed words. And of course you can augment the data and all that. But the comparisons presented by the motivating paper from NIPS, it's not even close. So I can give you that reference. Did I sufficiently address, or did there some aspect that?
You could use, there are obviously other ways, and I'm just wondering, what the trade-off is to go in this particular.
So the stuff I mentioned, none of the word level models that we built were robust to those issues. But there may be a way that I'm happy to talk about to you. Thank you.
Is language independent or only works with English?
No, it's language independent. Again, the only thing we're doing is we're taking the text, whatever the character is. If it's an image, that's fine. If it is, a Chinese character, that's fine. If it's English, if it's Russian, still, it's a character level signal that we are just training the model on. And, we are doing some work on explainability to try and explain why it works, right? We're all doing that, I'm sure, in our projects. But we haven't done that yet, but it's on the map.
So you're saying that it doesn't matter what language we train the transfer model in, and then we can apply it to whatever language?
That's not, so the architecture is transferable, right? So you probably will have an easier time doing the initial experiments in the space you're finally interested in, right? As much as you can't always do that. But I would hypothesize, or I would conjecture now that, it makes it harder if the language for the initial training was different, but it's still not impossible. That's a conjecture.
If you keep training, it'll eventually get used to the language change.
Yes.
What about the, like a medical doctor language, they are different, they use a different codes and stuff like that. For the same, like if you say heart attack, they use a different word for that. So how does it detect similarity?
So again, we haven't tried it, but my suspicion is it doesn't matter. That again, it was able to predict the class of a string, whether it's a number or it's like 5 numbers and therefore it's a zip code, right? So it doesn't really matter what the characters are. It doesn't really matter what the language, provided it's being used consistently and is predictive of your categories, the network should be able to pick it up. And I'll be happy to talk to you if we can find a way to actually prove that and not, wave our hands. But that's my conjecture.
Would you mind providing an example, just one instance where the use of character-based approach was, more efficient or more effective than using a word-based approach? I mean, because if it's, teenagers, you can capture the slang that they're using as words, right? But why was the, give an example that shows where character-based was stronger than using a word-based approach?
So it depends on what is the word level model we are comparing to. How is it generating the features? Do you have one particular one in mind?
No, I just.
I can just come up
Use
with
the
one.
example right from you.
Yeah, so if I use the word-to-word example that I've been running with in this conversation, if when you're generating the features, you probably pull, some pre-trained model, and then you try to generate, vectors for the words, right? But when it was trained and put online, it was trained probably on the dictionary or something like that, or maybe Wikipedia. It wasn't trained in an environment where, people are coming up with a new word all the time or using it differently, right? So those vectors aren't very reliable anymore. You could repeat the experiment and you could retrain the model in that space. You could retrain on that data, but you have to do it every single time, right? And there are some aspects of it you're going to have to, some hyperparameters you're going to have to pick, right? Now, what I'm saying is this model that you don't need that, right? You can just treat the signal as the characters as a raw signal, no matter what it is, without worrying about, all those hyperparameters, without retraining some model again, and then it becomes complicated. Take one architecture, whatever your problem is, it's robust to those kind of things. Well, if there are no more questions, we'll be around until our time's up to chat with you if you want. Thank you for coming.